Alright, so today we are looking at the structure of the cogebra of our universal enveloping algebra as from this biogebra structure we defined last time. We're looking at the universal algebra of G as now a cogebra. I'm guessing we're going to be adding on this this biogebra structure, then taking off the algebra. I'm doing this in characteristic 0, so we're doing this all k is characteristic 0. So we're going to let SG, of course, be the symmetric algebra of G. Symmetric algebra of G as a vector space. With CS, its coproduct with a reference to a book I do not have access to, and eta, the canonical isomorphism of the vector space SG onto U with eta of the product of x1 through xn. So we have to index, make sure index goes to n, is going to be equal to 1 over n factorial of the sum across T in the symmetric group, the sum of the products of all sigma x t I across I for x in G, we and n positive, non-negative of course, that eta of x, n copies of x, is equal to sigma x to the n. With eta then being unique by another proposition we don't have access to. This brings us to our first proposition. For every integer n non-negative, let U to the n be the vector subspace of U generated by the sigma x to the n for x in G. Part A states that U to the n is a graduation of U compatible with the existing cogebra structure on it. Part B says that the canonical mapping from eta from SG to U for U graded as above is an isomorphism of graded cogebras. And the proof, I'm going to pick an x in G, an n be natural, I believe, Don't know why they're using that all of a sudden, but I'm all for it. Then the S coproduct of x to the n is the S coproduct of x to the n is x tensor 1 plus 1 tensor x to the n, which is the sum from 0 to n. You know, that's the old binomial x to the I tensor x to the n minus I. But because it's, and we get this first equality because it's a homomorphism. Similarly, we get that c of eta of x to the n is c of sigma x to the n is c of sigma of x to the n, which is sigma of x tensor 1 plus 1 tensor sigma x to the n, which is, as above, the sum from I equals 0 to n of n choose I of eta of x to the I tensor eta of x to the n minus I. So that eta tensor eta of cs of x to the n is equal to c of eta of x to the n. As the x to the n generate SG, we then have that eta tensor eta on the S coproduct is the coproduct of eta. So eta is a cogebra isomorphism. We also see the eta of s to the n of g is u to the n, and so we're done our proof. Given that all these structures here are now compatible, now the graduation u to the n of u is called the canonical graduation. This comes with a corollary. The canonical mapping sigma defines an isomorphism of G onto the Lie algebra of primitive elements of the universal algebra. And the proof SC plus is a graded homomorphism of degree 0 PU. Yeah, we're going to run into that joke at some point. The primitives of the universal algebra is the sum of the primitives of the universal algebra with each u to the n, so it intersects at some point. It suffices to show that if n is greater than 1, and a in un is primitive, then a equals 0. Now we're going to write a as the sum of lambda I ai to the n for lambda I in k, ai in sigma g. By our previous result, the term of by degree 1 common n minus 1 in C plus a is n times the sum of lambda I ai tensor ai to the n minus 1 across our I, of course, which means that this sum without the n in front, lambda I ai tensor ai to the n minus 1 equals 0. If the map mu from u tensor u into u is defined by multiplication on u, then a is, as before, the sum across I of lambda I ai to the n, which is mu to the sum of I of lambda I ai tensor ai to the n minus 1, which as is from above 0, and so we're done. Now we have some remarks. First off, we see that u sub n is the sum of I from 0 to n of u to the I. Secondly, we see that eta is the unique morphism of graded cogebras of a symmetric vector space of n into u such that, well, such that eta of 1 is 1 and eta of x is sigma x for all x in G. I'm going to show this. Let eta prime be such a morphism. We show by induction eta prime of x to the n is equal to eta x to the n by induction on n. As we have from before, that CS positive of x to the n is the sum from 1 to n minus 1 of the binomial terms of this expansion x to the I tensor x to the n minus I. We get that eta tensor eta of CS positive x to the n is the sum of eta prime tensor eta prime of our CS positive of x to the n by the induction hypothesis. So we get that C positive, C plus of eta of x to the n is C plus of eta prime of x to the n. So eta x to the n minus eta prime x to the n is a primitive element of degree n, and so is 0. Now for part 3, let phi be the canonical isomorphism from Ts of G into S of G. The canonical isomorphism. The mapping then of eta composed with C of Ts of G into U is called canonical. It is the unique morphism, which we're going to call eta prime, of graded cogebras such that graded cogebras Ts of G into U such that eta prime of 1 is 1 and eta prime of x is sigma x for all x in G. Number 4. Let V be a vector space. The primitive elements of the bialgebra of the symmetric algebra V are the elements of degree 1, elements of degree 1, which comes from the corollary from a previous proposition applied to the commutative Lie algebra V. Alright, now let EI be a basis of G as a vector space, as a K vector space. With totally ordered indexing set I. For all alpha being natural numbers indexed by I, we write that e to the alpha is the product along the indexing set of sigma e sub I to the power of alpha I divided by alpha I factorial. The E sub alpha for size less than n, or equal to n, form a vector space basis of the vector space, the K vector space U sub n, then our E0 is 1, and E epsilon I is sigma EI for every I in our indexing set. This is going by, I'm going to say this is going by a lot faster than I thought it would. Once again, though, we're going to have to end at the end of this chapter, so we'll go through this page. Let me just verify exactly. As the graded algebra associated with the filtered algebra U is commutative for alpha and beta in the naturals indexed by I copies of the naturals, we get that E alpha times E beta is congruent to, this is a function we will define in a minute, double bracket of alpha and beta times E of alpha plus beta mod the U, the infiltration size of alpha plus the size of beta minus 1, where double bracket of alpha and beta is equal to the product along I of alpha I plus beta I factorial over alpha I factorial times beta I factorial. Just to make the combinatorics line up. We then get immediately that eta of epsilon 0, the counit of epsilon 0 is 1, and the counit of E alpha is 0 for alpha being at least, having size at least 1. Also, we see that for alpha in the naturals indexed by I, we get the coproduct of E alpha is the sum across beta plus gamma equaling alpha of E beta tensor E gamma. Which lets us determine the algebra U prime being equal to the homomorphisms of the hom of U on K, which is of course going to be the dual to the cogebra U. So we're going to let K of xi for I in our indexing set be the algebra of formal power series in indeterminates xi for I equaling I and I. If lambda is a homomorphism of u into k, then let f of lambda denote the formal power series f lambda equaling the sum across alpha of the rank bracket of lambda and e alpha times x alpha, which is our indeterminate. It's meant to be capital everywhere, but I mess it up, where this x alpha is the product along I in our indexing set of x I to the power given by the list of alpha. For alpha running through the natural numbers indexed by I, product of the natural numbers indexed by I. This leads us to a proposition, which is that the mapping of lambda to its equivalent formal power series, f lambda, is an isomorphism of the algebra U onto an algebra isomorphism of U prime onto the algebra formal power series of k in indeterminates xi for I across I, across our indexing set, of course. And the proof since our E alpha is a basis of U, this mapping from lambda into f lambda is k-linear and bijective. Then we see that for lambda mu in U prime, we get that f lambda mu is the sum across alpha of lambda mu bracketed with the alpha of x to the alpha, which is the sum across alpha of lambda tensor mu with c e to the alpha times rx alpha, which itself is equal to the sum across alpha of lambda tensor mu with the sum across beta plus gamma equaling alpha of e beta tensor e gamma times our string of determinants indexed by alpha, which is equal to the sum across beta and gamma of lambda with e beta times mu with e gamma times x to the beta plus gamma, which is just f lambda times f mu. So we have an isomorphism. And we're done our proof. And despite its length, this was a lot shorter of a video than I thought it was going to be. I mean, you know what? I don't want to put out like 3 half-an-hour videos. I'm going to do something dumb, and we're just going to finish off the chapter here. So we're also going to look at the structure of filtered bigebras in characteristic 0. So once again, we're working over a field of characteristic 0. You see, first off, if E is a bigebra, the canonical injection of the primitives of E into E can be extended to a bigebra. Yeah, B is a bigebra, not a bijection. Bigebra morphism Fe, which is a map from the universal algebra of the primitives of E into E. So it's off with this theorem. Let E be a commutative bigebra. Well, part A. The bigebra morphism Fe is injective. B, if E has a filtration compatible with its bigebra structure, Fe is an isomorphism. It's surjective, essentially. In case B, E is therefore identified with the enveloping algebra of the Lie algebra of its primitive elements. So we're going to start things off by letting CE and epsilon E be the coproduct and counit of E. We're going to write G to be the primitives of E. Let EI be a totally ordered basis of G as a vector space as before, and let E sub alpha for alpha in and I as before. It's probably good that we did this as a double video. Now we're going to write X sub A as being the image of E sub X sub alpha is the image of E sub alpha under Fe, for alpha being a natural number indexed by I. So we have that the counit of x0 is 1, and the counit of x alpha is 0 for alpha at least 1. We have the coproduct of x alpha as the sum of beta plus gamma being alpha of x beta tensor x gamma for alpha in the naturals indexed by I. As Fe is a cogebra morphism. We get that Fe is injective, which is our first theorem. From the following. Lemma. Let V be a vector space, E cogebra, and F the symmetric space of V into E a cogebra morphism. If the restriction of F to S0 of V plus S1 of V is injective, so is F. Alright, so for a proof of this lemma, we're going to let n be natural. Right, Sn as being the sum of I greater than n of Si of V we're going to let Cs be the coproduct of S of V and show by induction on n the restriction of F to Sn, I believe, is what they're trying to write there in a very weird way in the book, is injective. Now, it's trivial for our base cases, so let n be at least 2, and u in Sn such that f of u is 0. And then we get that 0 is the E coproduct of f of u, which is the tensor of f with itself, f factoring on both sides of the S coproduct of u, which is f u tensor 1 plus 1 tensor fu plus f tensor f, f on both sides of Cs positive of u. And we see that these two terms will cancel, vanish, so we get f tensor f of Cs positive of u has to be 0. As Cs plus of u lies within Sn minus 1 tensor Sn minus 1, by the induction hypothesis we get that u is primitive in SV, and so is of degree 1, and so is 0 as f sub s1v is injective. Now we see that's the family. We also see from this lemma, now that we've done the proof, that x sub alpha is free. We will show f sub e is surjective if e has a filtration compatible with its cogebra structure. So we're going to let E sub n be such a filtration and En positive, En plus be the intersection, the elements of En inside the kernel of the counit. We show by induction on n that each En plus is in the image of Fe. As E is k on 1 plus the union of our En positive, this will show that Fe is surjective. This, and we already have it shown for n equals 0 and 1. So we're going to let n be at least 2 and x be in En positive. We have seen that Ce plus of x lies within the sum from I of 1 to n minus 1 of ei plus tensor e to the n minus I plus. And by induction hypothesis, there exists scalars alpha, beta, for alpha and beta, of course being n indexed by I, which are cofinitely 0, so finite or non-zero, such that Ce plus of x is the sum for alpha and beta being non-zero of lambda alpha and beta of x alpha tensor x beta. Hence, by previous formula, we have that Ce plus acting on the left of Ce to the E positive E plus coproduct of x the plus coproduct in E of x is the sum for alpha, beta, gamma being non-zero of lambda, alpha plus beta, and gamma of x alpha tensor x beta tensor x gamma. And conversely, the same thing, but taking the positive coproduct, the plus coproduct in E on the right of the plus coproduct in E of x gives us the same construction, except that lambda of alpha and beta plus gamma of x alpha tensor x beta tensor x gamma thus, by our previous proposition, and by linear independence of x alpha, we get that lambda of alpha plus beta gamma is equal to lambda of alpha with beta plus gamma for alpha, beta, gamma in the naturals indexed by I minus 0. And by commutativity, we similarly get, through the same process, we get that lambda of alpha comma beta is lambda of beta comma alpha, not plus comma, for similar alpha and beta. Suppose there exist scalars mu sub alpha with alpha being at least size 2, such that mu of alpha plus beta is equal to lambda of alpha beta. Then C plus in the plus coproduct of E in E of x is the product of the sum for non-zero alpha and beta of mu alpha plus beta of x alpha tensor x beta, which is the sum for gamma being at least 2, size 2, of mu gamma times the plus coproduct in E of x gamma. So our y being equal to x minus the sum for gamma at least 2 of mu gamma x gamma is primitive, and therefore in the primitives of E within the image of f of E. Hence we have that x is then equal to y plus the sum for gamma at least 2 of mu gamma f e of e gamma in the image of f sub e. So we finish with the lemma. with a lemma. If a family of scalars lambda of alpha and beta is above finite support satisfies our previous conditions of lambda alpha plus beta comma gamma equal lambda alpha beta plus gamma, and lambda of alpha beta being equal to lambda of beta alpha. Then there exists a family mu alpha with size of alpha being at least 2, finite support, such that mu of alpha plus beta equals lambda alpha for lambda alpha beta for non-zero alpha and beta, of course. In the proof, we need that alpha plus beta equals gamma plus delta implies that lambda of alpha beta equals lambda of gamma delta by Reese, don't know how to say his name, decomposition lemma. There exists mu, rho, sigma, and taf in being sequences of natural numbers indexed by I, such that alpha is pi plus sigma, beta is rho plus taf, gamma is pi plus rho, delta is sigma plus taf. Now suppose that pi is non-zero, sigma plus beta is equal to rho plus delta. We get that lambda of alpha beta is equal to lambda of sigma pi plus sigma beta, which is lambda of pi less sigma plus beta, which is lambda pi rho plus delta, which is lambda pi plus rho delta, which is lambda of sigma and delta. If pi is 0, then beta is gamma plus taf, and alpha, delta is alpha plus taf, so lambda of alpha beta is lambda of alpha and gamma plus taf, which is lambda of alpha plus taf, gamma, which is once again lambda of delta and gamma, which is, of course, lambda of gamma delta. And we are finally done. Next up, we're looking at free Lie algebras. We briefly talk about magmas, but it doesn't look like they're covering what we've already seen in SARE, so hopefully there should be some new content there. Magmas seem to be just a vague mention, so looking forward to that, I guess.